now we look into the boundary value problem. Okay, till now we were only talking about heat equation on the whole real line, so the domain was unbounded, okay, had no boundary, and their only initial condition was given. But here we are going to address the question where some boundary condition is also given. For example, heat propagation on a finite rod. So earlier, all the time we were talking about only finite rod, and imagine that two different endpoints has certain heat condition, possibly a sink or source is there. Okay, so for those cases, this part is relevant. Here, let f be a function from 0 infinity to r, and this is Borel measurable. Okay, so here, why am I taking 0 to infinity? Because I'm not considering the whole real line but only the positive real line. This is a simple way to introduce a boundary, correct? Because here, I mean, it is lower bounded only. The simplest way to introduce a boundary. So that would be my domain. So now we are talking about the initial condition on that rod. Okay, so which is left hand side, it is bounded by 0. So there f is bounded Borel measurable, is not bounded, just a Borel measurable function, but has a growth property, because on the right hand side the domain is unbounded, f has plenty of chance to grow larger, but we put a condition that we do not want very large growth of f. We say that is 0 to infinity e to the minus ax square mod of f of x dx is finite for some a positive. Okay, so now under this assumption of f, we state the following: the probability that yt would be found, okay, in a neighborhood of y. Okay, so this condition actually, yes, so here I am not using f yet, I would use it later, but here it is very this is very important result, which is the consequence of reflection principle of Brownian motion. So let me elaborate. Consider this the probability of this joint event. What is this? The Wt, that means if you start from point x here at time 0, and then you just continue, and then this one dimensional Brownian motion moves on this line. Okay, and then it goes towards left, and then again comes to the right. And imagine the case when it moves to the left but does not cross 0, like this type of thing, that it goes left and then comes to y. Okay, so those events can be written as Wt in the neighborhood of y, whereas t0 is the heating time to 0, is greater than t. So at time t, Wt is in a neighborhood of y, but small t is less than t0. That means till time t, the Brownian motion did not hit 0. Is it clear? Okay, so this is joint event. So probability of this joint event given W0 is equal to x, precisely that it starts from x. If you add this probability with the Brownian motion at time t is in the neighborhood of minus y, and when given that is starting with 0, so these two addition of these two probabilities is equal to just probability that Brownian motion Wt would be in the neighborhood of y. Okay, so this is the reflection principle. So let me give a sketch of the proof of this identity. Now imagine that there are only two cases, that either capital T0 is greater than t or less than or equal to small t. Only two cases, correct? So imagine that it crosses 0 and comes to y. When it does that, okay, so then when it crosses 0, then we can reflect this path this way, this side. Okay, this is just horizontal reflection. When you reflect this path, then we get this gray color path. So from here to here, if you reflect along this this line, you are going to get this path, and that will land up exactly at minus y, because from here to here distance is y, so here to here distance minus y. And So for Brownian motion is concerned, that what does this reflection means, that at this point the Brownian motion, when it took the left hand move, you just reverse it to the right hand, okay, and then you just follow, okay. So that if Wt is a Brownian motion, minus Wt is also a Brownian motion, okay. This negative of that is also a Brownian motion. It is just the reflected part from this part to this part, whatever the process is, that if you just include a minus negative sign in front of that, you are going to get this thing from this point onward. So therefore there exists one path like this going to minus y, okay. So whenever it crosses, we can replace by this. So here that yt belongs to d minus, and to reach minus y from x, you have no other way than this. I mean, it must cross 0, okay. So if it reaches minus y at time t is fine. If it does not, it goes here, then we just reflect, okay. So probability that Wt is in d minus y, so a region around minus y, given W0 is equal to x, these two probabilities same as just this happens, because these are all possible cases. So all possible way to reach y is written in terms of two different separate events. One is that reaching y before hitting 0, another is that reaching minus y, okay. So this is the sketch of this proof of the reflection principle. We are going to crucially use this identity. So we are writing down this. So equivalently, the Wt is in the neighborhood of y, and T0 is greater than t, given W0 is equal to x. Just this term is equal to, now this I can take on the right hand side. So this probability is written in terms of the probability density function p of txy, okay, starting from x, reaching at y at time t, txy, but in the neighborhood here. So I have dy here, and from here I am going to get p of t comma x comma minus y, okay, because in the neighborhood of minus y dy, okay. So this conditional, the conditional probability of this joint event is written, we know that it has this density, the difference of ptxy minus ptx minus y, okay. So we are going to use this. Let us define u1. u1 is a new function of t and x. u1 of tx is defined as a conditional expectation of f of Wt, where small t is less than t naught, okay. So indicator function, okay. So when small t is more than t naught, that means that Brownian motion hits 0 before time t, so t0 is smaller than small t, then this part would be 0 and it would not contribute anything to the expectation, okay. So this conditional expectation we now would be able to, that is written as u1, and we would now be able to compute this expectation. Why? Because we know the density of that. So this is f of y ptxy minus ptx minus y, okay. From the last earlier slide, we know that this is the density, okay. So using that, this is integration 0 to infinity f of y 0 to, not minus infinity, because my domain is now 0 to infinity, f of y ptxy dy minus integration 0 to infinity f of y ptx minus y dy. So now here this is rewritten. So here just it is change of variable formula. So minus y is rewritten as y. So y becomes minus y. Here this changes this limit. Now if we introduce a new function f tilde, which is same as f on the positive line, but it is minus of f of minus y when y is negative, then see, I can talk about it, because if y is negative, then minus y is positive. So f is defined on the positive line. So I can talk about it. So then we can use this f tilde. Then this integration is nothing but f tilde of y minus infinity p of txy dy. and here we have minus infinity infinity, okay, full thing. And we know that what does it represent? It is nothing but integration. I mean, this is nothing but the expectation, because this PDF is appearing here. So it's the expectation f tilde yt, okay, given y0 is equal to x, because this is the density of wt. Okay, so f tilde of wt given w0 is equal to x. Okay, so we got one representation of u1 that is using this. Okay, so clearly f tilde also satisfies the growth assumption. See, here we had this growth assumption on f, correct? So it basically says the f cannot grow like e to the power ax square, because then this would be infinity, it cannot be finite. So this growth condition also puts condition on f tilde on the both sides here. So here you get minus infinity infinity, this is finite, okay, of f tilde. Okay, so it satisfies the growth condition, and we have already seen that when this is the case, then this this conditional expectation, when this satisfies the growth condition, then this conditional expectation satisfies the heat equation. So u1, which is defined in this manner, satisfies the heat equation, okay. And in addition to that, if we find out the limit, that what happens when t tends to 0 and y tends to x, etc., we would see that it would also be f tilde x. Why is it so? Because it inherits from the function f. We already had that, okay. So continuous and this, okay, and then limit u1 s tends to t, x tends to 0, okay, because 0 is the point when f tilde they mismatch, okay. So there, so that is 0, because here see, I mean, for y is equal to 0 we had 0, correct? Here 0, f tilde 0 is 0, so this is 0. So this t, I mean, from the theory what we have seen, that we can define for t from 0 to 1 over 2a. So for that we have this solution. Okay, so this whatever I have written in this fourth part, so that is also rewritten now again. I mean, exactly the same thing but in a different language, that u1 satisfies this heat equation and u1 ty converges there. So okay, so this is already I have stated. I mean, this part is important, that I mean, at the point of continuity of f, because everywhere this limit would not converge here, only to for those point x where f tilde is continuous, okay. So there it would converge. Now we talk about boundary data, okay. So I mean, till now I was talking about f was just initial data, my domain is bounded, so I should give some kind of boundary data here, okay. So here g is, so the boundary data should depend on time, correct, because the boundary remains boundary for all time. So how the boundary conditions are acting for each and every time, that you need to clarify. So here time is between 0 to 1 over 2a. So g is a function of 0 to 1 over 2a to r, is bounded continuous function that we assume here. So in short notation, g belongs to cb 0 comma 1 over 2a, and we define u2 of t comma x, okay, u2 of t comma x, that is conditional expectation of g of t small t minus t capital T naught t0 into indicator function of capital T0 to infinity. So here this small t is more than or equals to capital T0, given w0 is equal to x, okay. So there is a typo here, it should be open infinity, okay, it's not closed infinity, it's open infinity, okay. So ignore this reference. So what we do is that I mean, this reference is actually the reference page number of the book of Karajas and Shreve, okay. So there you would be able to find out this formula. So there is a typo, there is no 2 here, w0 is equal to 0. So what it says is that, so when you have a boundary b, okay, and w0 is 0, then you are asking that this distribution TB, okay, so like here T0 is the heating time to 0, TB would be the heating time to the point B for the first time. So that time is in the neighborhood of T, okay, dt. So that is a particular expression that is equal to mod of B divided by T times square root of 2 pi T e to the minus B square by 2T dt. Okay, so next we define one function H. So this H is basically the density of T naught. Okay, so probability that T naught belongs to dt given W0 is equal to X given and divided by dt. So this is of our interest. So here this we can rewrite in the following manner. Instead of thinking that Brownian motion is starting from X, you imagine the Brownian motion starting from 0, but then this would be Tx, because I mean X is here and 0 is here. So and Brownian motion starting from X and then hitting to 0 is same as the corresponding distribution would be the same as starting from 0 and hitting to X. Okay, so probability that Tx belongs to dt given W0 is equal to 0 divided by dt. So this is the place where we are going to use the above formula. Okay, so this is equal to, from this place, B, instead of B we are going to write down X. Here it is non-negative, so X, yeah, so T, and then this part would stand as PTx0, correct, because here we can see clearly that it is PTx0 if you replace B by X. So this we have already recognized that this is nothing but the partial derivative of P with respect to X. So here what we have obtained is an expression of the density function of T0, which appears here. To find out this expectation, it is important to know that distribution of T0 and density functions. So that is having this expression. Now we are in the stage, okay, of computing this expectation. So u2 of t comma x, okay, u2 of t comma x is expectation of gt minus t0, but we know the density of t0, so we write down that is the function of t0, correct. So write down g of t minus tau and then integrate with respect to the multiplied with the density of t0, that h of tau x d tau. Clear? Okay, so that we do, and since here t0 to infinity, okay, so I mean my small t would be, this t0 could be at most small t, correct. T0 could be as low as 0, but t0 cannot be more than t. If t0 is more than t, then this part is 0, correct. So I would integrate from 0 to t, small t. Understand? Because I am finding expectation where capital T0 is a random variable. So for that PDF I am using, but I cannot use T0 0 to infinity here, but because T0 can be at most small t. Okay. Now this is just a simple change of variable formula. You write down t minus tau is s, then you get here g of s h of t minus s x ds. Okay, and if t minus tau is equal to s, and if t minus tau is, if tau is equal to t, then t minus tau is equal to 0. So you would get 0 here, you would get t here, but with a negative sign, again you can change the limit upper and lower, you will get this value. We have already seen in earlier lectures that this del P del X solves the heat equation. Okay, so we are using that. Since u2 solves heat equation 2, so u2 of t comma x is equal to expectation of g of t minus capital Tx. So here you remember this T0 W0 is x, and then we have argued that we can write down W0 starting from 0 and this is Tx. So we are exactly doing that. G of t minus Tx, Tx to infinity t, here it is corrected, open interval, and W0 is equal to 0, okay, for all Tx. So this is an expression of u2. So what we have obtained, that u2 which has this expression satisfies the heat equation, that we have proved here, correct, from here, because that this H solves the heat equation, this integration solves the heat equation u2. So u2 also solves the heat equation, and it has this expression. Okay. Now what we want to take limit of u2 ty. Okay. So here since g is already given a bounded continuous function, we can do so, because here bounded continuous function is here, bounded function, and so we can do that. So limit s tends to t u2 of sx, okay, as x tends to 0, because 0 is the boundary. So x is coming from right hand side, here it is the space variable. So that is equal to gt. We are going to get it, because of we can actually take the limit inside. By taking limit inside, we are going to get, we can take limit inside because g is bounded. And also similarly, that when t is coming to 0, the initial stage. So let us see what happens when t is close to 0. Then if this capital Tx, whatever it is, when t is smaller, okay, so it would cross that. So that means this part would become 0, right? So for every omega, that that Tx would be some positive this thing, but small t goes to 0. So almost surely this goes to 0. So if you take limit inside, this whole thing would be 0. So u2 ty is 0. So here we can see that u2 solves, of course, the heat equation, and it solves this boundary condition, because as x tends to 0, okay, it satisfies the boundary condition. On the boundary it is g of t, and it satisfies 0 initial condition. So it satisfies, the initial condition is 0, so it starts with 0. On the other hand, when we have seen this u1 in the earlier slide, u1 that satisfies this heat equation, and here the initial, it satisfies the initial condition fx, but on the boundary, okay, so when y goes to 0, then it is 0. So that means it satisfies 0 boundary condition. So like here we have separated. So u1 and u2 are like capturing two different things separately, okay, isolately. Okay, u1 was capturing the initial condition, u2 is capturing the boundary condition, and both solve the same heat equation inside the domain in the interior. Okay, so that is a good thing. So we can just add these two. Okay, if we add these two, u1 plus u2, then we get u3. u3 would also satisfy the heat equation, because it is a linear PD. The addition of two solution is also a solution, and then the boundary and initial data both would be satisfied by u3, correct. So the new function u3 actually solves the initial boundary value problem. Okay, so this is the thing. So u3, now we want to write down u3. u3 is nothing but u1 plus u2. So u1 is written here, f of wt1 tx infinity t, and u2 is written here, g of small t minus t naught, indicator function of tx to infinity. Okay, so this expression combined, okay, this whole expression gives us the stochastic representation of initial boundary value problem for heat equation. Okay, so next we are going to see the interpretation of this expression. Okay, I mean, already we have seen when there is no boundary, it's unbounded domain, that how it means. So for bounded domain we are going to see now. Okay, imagine that we have chosen a point t comma x. Okay, and then so x is this, okay, and small t is here. Okay, so whole thing is a function of t comma x, and here we start a Brownian motion times 0 at point from the point x. So we start a Brownian motion from here and imagine the Brownian motion. So this is one path of Brownian motion which is moving, okay, and then at some point we see that, okay, possibly there actually for every point, I mean, you can go in many different spaces. So we just see only two paths. So one path is moving like this and coming here, and the path is coming like this and then going here. Okay, we call this above path is W1 and below path is W2. And then see that when I mean these W1 W2 are two different paths which has which I have chosen for a particular reason, because they do things differently. W2 hits the this time axis first, whereas W1 hits the x axis first and then time axis. Okay, so whatever the case is, okay, so what we do is that we find out this point. So this point is for the path W2. So this distance, this time distance is T0 W2, because this is the first time it reaches 0, because this is the x axis, correct? So this time axis, hitting time axis means that space becomes 0. For the first time that the motion reached 0, okay, so that is T0 W2, and this time point therefore small t minus T0 W2. Okay, so this time T minus W2. Okay, on the other hand, for W1, when it hits this time axis, then we are going to say that, okay, this whole thing is T0 of W1, and then this time point is T minus capital T0 W1. Clear? And when this W1 hits this x axis, then what happens? That means that it is like initial time, because t is equal to 0, correct? Here t is equal to 0. So initial time, hits the initial time point. Okay, so there, this point, the locus of this point is Wt of W1. Okay, why Wt of W1? Because W1 is the path, and this your Brownian motion started here, so it is the time 0, and then your clock started. So since this distance is exactly time t, you need exactly time t to hit here. Doesn't matter whether you go up or down, you need exactly time t to hit here. So when you hit here, then in your clock you have t time Brownian motion. So Wt of W1 is this point. Okay, of course this is a random variable. Okay, so now we see this slide here. F of Wt when small t is more than Tx. Okay, here it should be x, there is a typo, g of small t minus Tx. Okay, so if I write down W0 is equal to x, then it should be 0, it should be 0, it should be 0. Okay, so there is a typo that I should write down 0 0 here. Okay, if I write down 0 here, then I should write everywhere x. Okay, clear? So it should be 0. Now, so these are the two different cases. So now for W1, here T0 W1 is more than t, small t, correct? T0 W1 is more than small t. So this part would be 0, because T0 is more than small t. Okay, so small t is, or in other words, small t is less than T0. So this part would be 0. So this part would contribute only. Okay, here it should be open 0 comma T0. Okay, there are many typos here, so let me write down on this T0 comma infinity. Okay, and other things are all correct. Okay, so this part is wrong. Okay, open 0 comma T0. So here, when let us go back to the picture here, when we talk about W1, so in W1 capital T0 W1 takes more time from here to here. It is of course longer than small t, because small t is from here to here. So here we would, so capital T0 is longer, so therefore small t of this is 1. So this part would survive here. So it would pick up the f of Wt. However, for W1, since T0 is longer, so this would be 0, so G function would not appear here. So for W1, we are going to consider f. F would only appear, so f is initial condition, so f appears here, correct? I mean, f is given on this line, because this time t is equal to 0 line. Okay. On the other hand, for W2, when T0 is smaller than small t, because T0 is smaller than small t for W2, then this part would not contribute, because small t, I mean, is more than T0, this integrator function would give you 0, whereas here you are going to get a non-zero value. It would be 1, and then g of t minus t naught would be there. Okay, so and g is defined on the boundary. So this t axis is the boundary of x, correct, all the time. So it's clear, correct? So it is now clear that what to do if you want to find out this, this U3 using simulation, for example. Okay, so you just generate the Brownian motion, if it and check which part does it hit first, this line or that line. Wherever, so if it hits this line, then at this point you compute g function. If it hits this line, then at this point you compute f function, and all these values you just take, add and average. Okay, you just average all these values, that's it, nothing other than that. Okay, so here, I mean, at this point you have to evaluate the function g of t minus t, that amount of time it is required, correct? So and then you average, and then that would be an estimator of U3. Okay, so that much just I wanted to say. Thank you very much.